don't know enough codes yet to write a complete program. So in this lesson, we'll learn a few more codes, relatively simple ones, but nonetheless, they'll help us to write a complete program. Every program begins with a program label. The program label code is the letter O. Sometimes you'll see the character colon used for this purpose as well. The program label would consist of the letter O, or the colon character, followed by a 4-digit number. Notice that this is a whole number and no decimal points are allowed. At the end of the program would be the M30 command. The M30 is the program end or program stop command. This command will also rewind and reset the memory of the control so that it can run another cycle. So therefore, each program will begin with the letter O and it will end with an M30. Here you can take a look at a complete program. Begins with the program label, O1997, calls up tool 1 with offset 1, TO101, turns on the spindle at 220 surface feet per minute in the forward rotation, G96, S220, MO3, rapids to an X position of 1.35 inches and a Z position of 0.1 to the right of program 0, and turns on the coolant with the command GOO X 1.35, Z 0.1, and MO8. The next line, GO1 Z0 F.005, feeds the tool to Z0 at a feed rate of 5 thousandths per revolution. The next command, X minus 0.03, would be a facing cut, moving the tool down the front of the workpiece. G00 X 1.25 Z 0.05 moves the tool up to a diameter of 1.25 inches and the tool to the right of the face of the part at a Z position of 0.05. GO1 Z minus 0.875 takes a turning cut along the diameter of the part to a length of 0.875. The next command, X 1.35, will feed off of the workpiece to a diameter of 1.35. G00 Z.1 MO9 will rapid the tool back to the front of the workpiece and turn the coolant off. G28 U0W0 will zero return the tool in both the X and Z axes, and it will send them to the home position. And finally, the program ends with an M30. Each line in the program really should have its own unique name, just as each program would have its own unique name using the O word. For the lines in our program, we can use the N word, which specifies a line label. This would appear at the beginning of each line in our program. The N word can consist of a 4-digit number without a decimal point. It is not important to put the leading zeros in, as shown in some of the examples toward the bottom of the page. However, if your programs in your company are created by a computer, you will often see them output the full 4 digits with those leading zeros. You will notice in the example program below that the O word does not have a line number, nor does the M30. The O word should always be on a line by itself, or if there is something on that same line, it should be in what are called parentheses. We'll talk about those a little bit later. The M30 can have a line number, but oftentimes you will see it on a line by itself. This is just a programming style, and it adds to clarity for that M30 command. When selecting line numbers, you can count by ones, or if you go on to the next page, you could count by fives. Or, going on to the next page, you can count by tens. It really doesn't matter which numbering sequence you use. Those numbers are there only for reference. The control does not execute them in order or anything like that. They are strictly there for the purpose of helping a user to read the program and for organization. The whole purpose of the line labels is to help you organize your program. With each line having its own unique name, you can easily search through the program and find the exact line you are looking for. This is very beneficial to the setup people when they are setting up a job and they need to change a feed rate. Sometimes you'll have to change a feed rate or a speed when setting up because the cutting conditions aren't quite optimal. In that situation, if the setup person just searched for F commands, he could accidentally change the wrong feed rate because there are many F commands within the program. But if he's running the machine and he looks to see which line number that F command is on, he can then search for that line number containing the F word, then go over and alter that F word knowing that he's got the exact one that he needs to change. So basically, line labels are there for the purpose of organization and for ease of use out on the shop floor, as well as by programmers when editing these programs. There are times when we need the machine to stop for certain things. During setup, you may want to stop the machine between each tool so that you can check the size of the part before allowing the machine to go on to the next tool. Doing it this way, the setup person can almost always get the first part correctly on size. Also, during production, there are times when you may need the machine to stop for some manual function. Adding tapping compound to a tap, for example, is one situation where you need to stop the program every time. Another possibility would be a thread rolling die. Thread rolls oftentimes need to be manually reset before the machine can cycle again. So that would be an excellent example of when we need to stop the program every time mid-cycle. Depending on the situation, sometimes you may need the machine to stop optionally, and in other cases you need it to stop every time. For an optional stop, we have an optional stop command, M01. On the operator panel of the machine, you will look for a switch called optional stop. When that switch is turned on and the command M01 is executed, the machine will stop execution. This allows a setup person or an operator to open the door of the machine and check on something. If the switch is turned off and an M01 command is executed, nothing happens. It is basically just skipped over. So the M01 command is very helpful for the setup people as well as operators. A good place for this command within our programs is between each tool. That gives the operator or setup person an opportunity for the machine to stop optionally between each tool for workpiece inspection or for any other purpose. In the example program shown here, you can see the M01 command on line number 110, just before the tool change command calling up tool number 2. If the optional stop switch is turned on and this program is running, when it comes to line number 110, the machine will stop, and that allows the setup person to go into the machine and check the workpiece. Notice that there isn't an M01 command before the M30. It doesn't make sense to have an optional stop before the program end. Let's watch this program run through its entirety. At the end of the cycle, the machine will stop. If you want to run the cycle again, just click on the Cycle Start button below. Notice also that the optional stop is shown as off. On the next screen, we'll turn the optional stop on and provide you with an opportunity to see how the machine would run in that situation. Notice when this cycle runs, the tool will come in, turn and face the workpiece, and then the turret will go back to the home position and just stop. If you click on the Cycle Start button, the program will then be allowed to continue on past that MO1 command. Run it through a few times so that you get the hang of it. The M00 command is a program stop command. It is used anywhere within the cycle to stop the machine for a manual operation. Some examples would be a flip job. A flip job is a part where you run the first and second operation consecutively. After first running the first operation, the machine would stop at the M00 command. You would then take the part out, flip it around end for end, put it back in the chuck, and then run the second operation. Another example would be removing chips. Some materials cut very poorly and you have terrible chip control. The chips can pack into a hole after drilling or boring, and they may need to be manually removed. Other possibilities would be in a tapping situation where we need to add a tapping compound to the tap before the tap is allowed to actually cut the workpiece. These conditions, and there are many more, require the machine to stop every time and without an option. So when the MOO command is encountered by the program, the machine will just simply stop. After the MOO command, it is important that you add in all the commands necessary to get the spindle back running again and to continue on with your cutting operations. This is a good program example to study. This program example will show a turning tool coming in and facing off the part and turning it, which we've seen many times so far. Then tool number 2, which is a drill, will come in and drill the workpiece. We haven't seen a program example of this yet. Finally, tool number 3 is a tap. You will notice that for a tapping operation, we have to start out the spindle in forward rotation, as noted on line number 200. Then we rapid the part to X0 and Z of 0.25. The next command, GO1 Z minus 0.625 at a feed rate of 0.0833, is how we feed the tap into the workpiece. Now, because a tap is actually screwed into the workpiece, we have to stop the spindle, as shown on line 230, reverse the spindle, as shown on line number 240, and then we have to feed back out of the hole, unscrewing the tap from the workpiece, as shown on line number 250, GO1 Z.25. This is a good example of tapping on a CNC lathe. There is no automatic cycle to handle this. But what we really wanted you to see at this point was line number 180 with the M00 command. When this cycle runs, it will stop at the MOO so that the operator could put a tapping compound on the tap before the tapping operation actually occurs. Let's learn about a few more commands here that are very, very helpful, but their name is a little bit odd. These commands are called the control in and control out commands. They allow us to have the control skip over stuff within the program. The left parenthesis key is the control out character. When the control is reading a program and it encounters that left parenthesis, everything after it will be ignored until the control in character, which is the right parenthesis. By using these codes within our program, we can include all sorts of descriptive data. Within the program, you can include setup instructions, operator instructions, tooling lists, warnings about certain conditions, and just about anything important to the program or to the setup person. Here is a program showing the minimal use of these comment characters. Notice that on the program label line, there is the comment characters with the part number and a revision number in it. This is a good place for that. If you use these comment characters on the program label line, when you do a directory or a library listing on the CNC control, the information in those comments will show up with the program label. This is helpful to setup people and operators. Then, located throughout the program is various descriptive data about when the program was written and what each tool is, with an accurate description with not only the tool holder, but also the insert grade that should be used with that tool. All around these comment characters, or as they are technically called, control in and control out characters, are very helpful for documenting CNC programs. Some companies utilize the comment characters completely for their layout information. Rather than having a separate document describing the setup of this particular program, they include everything within the CNC program using these comment characters. It is advisable in today's situation where more and more companies are going to paperless automation or paperless factories that you try to utilize features like this more and more. However, you should note also that not all of the controls allow you to type these characters on the machine. Most controls today, especially the 3T and 0T controls, do not have the control in and control out characters on their keyboards. So these comments actually need to be typed off of the machine tool by using a computer. Let's take a few minutes to introduce you to Tool Nose Radius Compensation, a very powerful feature that can save you hours and hours of manual calculations. When we are writing our program, we are treating the tool as if it had an actual sharp point on it. But as you may know, all tools have a radius on them. If the tools were ground to a sharp point, that point would probably break off very quickly when cutting the first workpiece. Therefore, all carbide insert tooling has a radius on it. Now, most of the radii that are on these inserts are in the range of 15 thousandths to 31 thousandths. However, in special circumstances, this radius can be as small as 3 thousandths of an inch, all the way up to 3/8 of an inch, and even larger on big equipment. Now, the thing that you have to understand, what we are programming is that theoretical sharp point of the tool. To illustrate to you the difference between programming the theoretical sharp point of the tool and the radius of the tool, watch this animation run. Now, keep in mind, we are always programming and positioning that sharp point of the tool. I want you to watch closely to see what part of that radius on the insert is actually coming into contact with the workpiece. As you watch this animation again, what we have done was highlighted the area on the workpiece that is not being cut by the radius of the insert. Now, you must understand, tool nose radius compensation cannot cure this problem. This is strictly a limitation of the tool, the physical capability of that tool to cut an inside radius. Now, on this animation, the radius of the tool is greatly exaggerated, but we are talking about a very precise machine, and therefore our programming of it must be very precise. Now, on these inside radii, you will see on a blueprint it will specify that there's a minimum inside radius allowed. Well, that's what would dictate to you what radius insert you can use on this particular workpiece. With this animation, you can clearly see the difference in positioning between having tool nose radius compensation turned on and off. To run this animation, click one of the gray buttons below, either labeled TNRC off for tool nose radius compensation off, or TNRC on. Run these several times until you see the difference in positioning of the tool. When tool nose radius compensation is turned off, you will notice that as the tool cuts along this chamfer, the radius portion of the tool never actually contacts the workpiece. This would mean that our chamfer would be smaller than what is required. There would be too much material left on the workpiece. But the theoretical sharp point is going right along our program path. Now, when we turn tool nose radius compensation on, the tool will be shifted. All of the program commands will be shifted to accommodate for that void between the programmed point of the tool and the radius of the tool. Watch again several times on this animation. We will also show you on the next slide how this affects the machining of a radius. Here again, you have the opportunity to run this animation with tool nose radius compensation turned off and with tool nose radius compensation turned on. Run it several times, and again, look to see where the programmed point of the tool, that theoretical sharp point of the tool, see where that follows along your programmed path, which would show up on the animation as the finished shape of this part. Now, when tool nose radius compensation is turned off, the theoretical sharp point of the tool follows right along the shape of the part, which means anywhere along that radius, we would not have cut enough material. When tool nose radius compensation is turned on, you will see that as the tool is machining that radius, the theoretical sharp point of that tool is shifted inside the boundary of the finished shape of the part. Again, tool nose radius compensation is compensating for that radius on the insert and the difference between that radius and the theoretical sharp point of the tool. Here again, watch two different animations, one with tool nose radius compensation off, and the other with tool nose radius compensation turned on. What you should see is that both tool paths are identical. Tool nose radius compensation does not shift the programmed path when we are machining on a single axis only movement. If you look at this example, we are moving only on the x-axis or the z-axis at any given time. In the previous two animations, when we machined the taper or chamfer, and when we machined the radius, both the x and the z-axes were cutting at exactly the same time. That is when tool nose radius compensation has to modify the tool path for us to accommodate for that difference between the theoretical sharp point and the actual radius on the tool. To help you see this a little bit more clearly, look closely at this diagram. You will see that there's a blue shaded area coming from the theoretical sharp point of the tool back towards the radius of the insert. That is what tool nose radius compensation is actually compensating for. At any time that the tool is cutting along that red line on the insert, that is when tool nose radius compensation kicks in and modifies our programmed tool path. This can actually only occur when the tool is cutting along the X and Z axes at the same time. Now, fortunately, tool nose radius compensation is rather smart in that we can turn it on at the beginning of a machining operation, and it will just simply calculate a new position whenever required. So in other words, we turn it on at the beginning of a machining operation, and then when we get done with that machining operation, we would turn this feature off. And it will handle all of the delicate little details and the very complex mathematics for us automatically. Not all tools and machining operations require the use of tool nose radius compensation. The purpose for tool nose radius compensation is to ensure the accuracy of the workpiece when we are machining a taper, a chamfer, or a radius. Thus, it is really not important to use it in roughing operations. It would serve no purpose, as the roughing operation, when used without tool nose radius compensation, would leave extra material for us to machine with the finishing tool. Now, that extra amount of material would only amount to a few thousandths of an inch, so it is truly not very critical. When you are using tool nose radius compensation, you would probably use it with a finish turning operation, a finish boring operation, a finish facing operation that had a contour on it, not just simply a straight facing cut. And sometimes, in very critical grooving operations, you may need to use tool nose radius compensation there. It would not be important to use tool nose radius compensation when doing rough turning, rough boring, rough facing, and definitely never with drilling, reaming, or tamping, and definitely not with threading. Grooving, as we mentioned earlier, in very critical applications, you may need to use tool nose radius compensation. And for cutoff tools, it would be seldom, if ever, needed during the cutoff operation. By now, you probably understand why we need tool nose radius compensation. Now let's take a look at how we program it. Believe it or not, as powerful as this feature is, there are really only 3 codes that you need to learn. The G40 code turns off tool nose radius compensation. It is a modal command. The G41 command turns on tool nose radius compensation when the tool is to the left of our programmed path. G42 turns on tool nose radius compensation when the tool is to the right of our programmed path. Understanding this left and right is a little bit confusing for beginners, so we'll walk you through a few different applications between left and right. The trick to understanding the difference between G41, tool nose radius compensation left, and G42, tool nose radius compensation right, is understanding how the tool is approaching the workpiece. If we watch this animation run through several times, you can start to get the understanding of it. Here we are showing you a finish turning operation on this workpiece. Notice how the tool comes into the front of the workpiece and moves along the outside diameter of the part. The second time the animation runs, the part will disappear and just the programmed path will show up. Now look in the direction of that programmed path as indicated by the arrow at the end of it, and look to see which side the tool is on. If you are looking in the direction of the path, or in other words, the direction of cut, you will see that the tool is on the right-hand side of that path. Now let's take a look at how that code would fit into the program. Below, you'll watch the animation run, but at the same time, try and follow along with the program. You will see that on line number 25, there is a command G42. That is turning on tool nose radius compensation. Now, tool nose radius compensation is modal, so we really only need to turn it on at the beginning of the contour. Then it remains active all the way through the finish turning operation. On line number 65, when the tool is moving away from the part along the x-axis, we are turning tool nose radius compensation off, as we don't want it active during any rapid motions moving away from the part or at any other time. Watch this animation closely and watch the program. Look it over carefully and try and follow along with what the tool is doing. What we want you to also see is where the tool nose radius compensation is turned on and where it is turned off in relative terms to the actual program and to the machining operation. You'll notice that when we turn it on with line number 25, we are not actually cutting the part during that motion. Granted, at the end of that motion, the tool nose radius compensation will be active, however, not during that motion. The same is true on line number 65. During that motion, we are turning off the tool nose radius compensation. But while we are doing that, we are moving away from the workpiece and not actually touching it or cutting it. When we turn the tool nose radius compensation on with either G41 or G42, we call this the approach move. We are approaching the workpiece but not actually machining it. When we are turning off tool nose radius compensation with the G40 code, we are moving away from the workpiece. This movement we call the escape movement. And again, we are not cutting the actual workpiece during this movement. Here again, you can see that same animation. This time I've moved the program path away from the workpiece so things are a little bit more clear. Here you can clearly see the approach move and the escape move. Now what you must understand, the approach move is only on the z-axis, and the escape move is only a movement along the x-axis. Now what you want to do whenever turning on tool nose radius compensation or turning it off, you really only want to move one of the two axes during that motion. It doesn't matter which axes, but you only want to move one of them. Another important aspect of the approach and escape is the distance the tool will travel. The tool must travel greater than the radius of the insert. If it does not, you may get an alarm. To review, we know that the approach move is the movement that turns on tool radius compensation. The escape move is the movement that turns off tool nose radius compensation. During the approach, we want to move along one axis only, either X or Z, and we want to move a distance greater than the radius of the tool. During the escape movement, we again only want to move either the X or the Z axes, and we need to move a distance greater than the radius of the tool. Determining which axes to move during the approach or the escape can be rather confusing, but let's try to simplify it as much as possible. Now, in this example program we see below, our approach movement is along the z-axis. The next movement is basically an x-axis movement, which starts out the radius going around the workpiece. That is how you would determine what you should do during the approach. What we look at is what is the machining operation being performed and in which direction. If we are moving the x-axis as our next machining operation, then we want our approach to be on the z-axis. If the next machining operation would be a movement along the z-axis, our approach should be done on the x-axis. Now let's look at the escape. If you look at the program closely, you'll see that we turn the diameter, and then the escape moves up away from the workpiece. So our last machining operation was along the z-axis. Therefore, my escape movement should be along the x-axis. It takes a little getting used to, but if you follow the examples here on the screen and in your workbook, I'm sure that you can start to see a similarity between how the approach and the escape is done for all tools and on all parts. On this particular machining operation, we are doing a finish boring operation. Again, we are going to use tool nose radius compensation, but this time we have to turn it on with G41. If you look closely and watch the animation, you'll see as the tool is cutting the workpiece, the tool is actually on the left side of the programmed path. Watch as the animation runs through the second time, and we will only show you a red line representing the programmed path. And notice that the tool is on the left of that line as we look in the direction of cut, which is indicated by a red arrow. We will then take you on the next slide to show you how this fits into the program. But basically the rules are the same as for the turning operation. We approach along the z-axis, turning on our tool nose radius compensation. And we perform that approach along the z-axis because our next movement is basically an x-axis movement to start out that radius. When we get to the end of the bore, our last machining operation was a z-axis movement, which means that we should turn off tool nose radius compensation with an x-axis movement along with the G40 command. Here you can see within the program for this tool that on line number 105, which reads G01, G41, Z0, F.0035, is where we're going to turn on tool nose radius compensation left. On line number 140, we are going to turn off tool nose radius compensation with the command G01, G40, X.875. This is a real good example of a finish boring operation using tool nose radius compensation. Here is the complete program showing you the turning operation and the boring operation. On line number 25, we turned on tool nose radius compensation right with the G42 command. During that motion, we were not cutting the workpiece, and we would be moving a distance greater than the radius of the tool. I can tell this by looking at the previous line, and the Z position there was 0.1. So to feed from Z of 0.1 to Z0 would have been 100,000ths of an inch movement, definitely greater than the radius of the tool we're using for this. On line number 65, you can see that we're moving away from the workpiece along the x-axis, moving to a larger diameter, and we are turning off our tool nose radius compensation with the G40 command. Now look on the previous line to this, line number 60. That was a z-axis movement. Because that was a z-axis movement, I know that line number 65 should be an x-axis movement when we turn off the tool nose radius compensation. Going on to tool number 3, you can see in line number 105, we turn on tool nose radius compensation left for this boring operation. You will see that the G41 command is used, and you will see that, again, we are traveling a distance greater than the radius of the tool, because the previous line was at Z of 0.1, and we are moving to Z0. Again, 100,000ths of an inch movement, which is going to be greater than the radius of our insert. Going back to line number 140, you will see that, again, we are going to cancel tool nose radius compensation using the G40 command, and we are going to move to a smaller diameter on x-axis so as not to hit the finished bore. The distance that we're going to move there is basically a 50 thousandths or so. We need to move smaller from the x.9375 diameter smaller to the .875 dimension. You might want to back up, rerun these animations, and watch these tools and how they react to the workpiece, and you may want to see how the basic motions occur. The approach and escape moves are very critical. If you follow the basic rules, they are going to work for you reliably time and time again. What we would like to show you now is how the tools can be applied to the workpiece different ways. Each tool can cut in several different directions, but basically as they apply to a workpiece and with relationship to tool nose radius compensation, the tool would basically either be to the left or to the right of the program path. Now when you study these diagrams, what we want you to look at are the red arrows. These red arrows will represent the cut direction. Now as I mentioned, the tool can cut in either direction. Now if you look at the red arrow, and then you look at the G41 or 42 next to it, you can kind of get an idea of which command you should be using. Follow along with each of these slides and see how that tool is applied and in which direction it's cutting. The trick here is to always look in the direction of the arrow and to see if the tool would be on the right of it or on the left of it while looking in that direction. In this particular example, we are looking at a turning tool. If we were to perform a normal turning operation, one that is going from the front of the workpiece towards the back, which would be to the left, the tool would be in a G42 situation. If the tool was cutting the opposite way, from the back of the front, the left, towards the right of the part, which would be the front, the tool would be in a G41 situation or a tool left situation. Here we are looking at a boring operation. A normal boring operation would occur when the tool is machining from the front of the part towards the back of the part. In that particular situation, the tool would be in a G41 situation. If the tool was back boring, going from inside the hole coming out towards the front of the part, the tool would be in a G42 situation. This would be considered a button tool, or sometimes they are referred to as a neutral or profiling tool. These tools are very universal in that they can cut efficiently either going to the left or to the right. Now if this tool were moving towards the left, as in a normal finish boring operation, it would be a G41 position. If the tool were moving to the right, as in a back boring situation, the tool would be to the right of the program path, meaning that we would need to program G42. Here you can see a back boring operation with a back boring bar. You can see the sharp hook angle on the insert, which allows it to cut very effectively when it is pulling out of a bore. However, this tool, as with all others, can go in either direction. If we were to utilize it as in a normal boring situation, it would be a G41. If we are to use it as it is designed, in back boring, where we are going from inside the hole coming out toward the front, its application would be G42 for tool nose radius compensation. Although this may look rather impossible, using a button tool or a profiling tool on the back face of the workpiece, there are certain machines that allow machining in this position. They are called subspindle machines. But if you look again at the direction of cut, the application of this tool with regard to G41 and G42 is the same as with all other tools. If the tool is moving up in this position, the tool would be in the left of the programmed path. Therefore, we would use G41. If the tool were moving down in this particular path, the tool would be in the right of the programmed path. Therefore, we would use G42. Here you can see a back boring operation with a back boring bar. You can see the sharp hook angle on the insert, which allows it to cut very effectively when it is pulling out of a bore. However, this tool, as with all others, can go in either direction. If we were to utilize it as in a normal finish boring operation, it would be a G41. If the tool were moving towards the left, as in a normal boring situation, it would be a G42. looking in the direction of cut, the tool would be on the right of that path, meaning that we should command G42. Here you can see a back turning operation. A back turning operation would refer to the tool cutting from the back of the part towards the front of the part. However, if the tool were moving towards the back of the part, it would be a G42 situation. If the tool is moving towards the front of the part, the tool would be in a G41 situation. Or in other words, the tool would be on the left of the programmed path. Here we can see that profiling tool that we showed you on the bore and on the back face being used on the diameter of the workpiece. These profiling tools are used quite frequently, but as mentioned with the boring operation, they are very flexible in that they can cut very efficiently, either going towards the left or towards the right. Here we can see that if the tool were used as a normal turning operation, cutting from the front of the part towards the back, we would use G42 as the tool would be on the right of the programmed path while looking in the direction of cut. If the tool were coming from the back of the part towards the front, we would be in a G41 situation, as the tool would be on the left of the programmed path. Here again is another profiling tool, this time applied to the front face of the workpiece. If the tool were moving... Now let's get back to a little bit more about the application of tool nose radius compensation. You will see that in our previous examples, we turned on tool nose radius compensation at the beginning of our contour, and then turned it off at the end of the contour. Now in those two examples, that was for the entire cutting operation of that tool. What I want you to look at on this particular slide is see how the tool comes in and performs a facing operation, then makes a rapid positioning move to position the tool properly to come in and finish turn the part. Now, as mentioned earlier, we really don't need to have tool nose radius compensation turned on for a straight facing cut because we're only moving one axis, the x-axis. However, when we are turning the rest of this workpiece, we would be making two combination moves, one to cut the chamfer at the front of the part, and then there is a taper midpoint along the turn. There we definitely need our tool nose radius compensation turned on. Another problem that could arise while you are programming this particular part is that if you look closely, when the tool is taking the facing cut, the tool would be in a G41 situation. Then as the tool repositions to take the turning cut, during that turning cut, it would be in a G42 position. That would mean that we've got a serious conflict. We would either have to turn it on and off for each of the different cuts. But that really isn't necessary, and it's truly not proper. Because again, we don't really need to have tool nose radius compensation turned on during that facing cut. All we really want to do is turn it on during the turning operation. To handle this, because it is such a common problem, because we take a turning tool and we will often face the part first and then come in and perform our finished turning operation, I've demonstrated to you in this program how this is handled, and it is truly quite simple and elegant. What we will do, between lines numbers 10 and line number 30, we'll have our tool startup information, positioning the tool ready for the facing cut. Line number 40 moves the tool over to Z0. Line number 50 faces the part off. And notice that when we face the part off in this example, we are going to a position of X minus 0.03. This is actually very proper. You want to feed past the center line of the spindle when doing a facing cut. That eliminates the little nib that is sometimes left on the center line of the part. Line number 60 is a rapid positioning move to bring the tool up into position so that our next movement, which is our tool nose radius compensation approach movement, is positioned properly. Notice that the Z.1 gets us 100 thousandths away from the front of the part. On line number 70, where we feed up to Z0, which is the face of the part, we will have a distance traveled of 100 thousandths, which would definitely be greater than the radius of the insert used for this turning operation. Then the tool would continue along its path all the way up to line number 120, where we are feeding off of the part, turning off our tool nose radius compensation with the G40 command. What you want to study here is how that the facing operation was performed without tool nose radius compensation, as it wasn't needed, and then how we reposition the tool to make that turning operation with the tool nose radius compensation turned on properly.